Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is a new episode of Turbulence at the Exascale podcast. So the aim of this podcast is to gather the view of the community regarding exascale computing for turbulent flows and what are the challenges and opportunities about exascale computing for turbulence research. So if you're not familiar with the UK landscape about exascale computing, the UK has recently launched a program called ExCALIBUR, which will run until 2025. And ExCALIBUR is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to deliver research and innovative algorithm development to harness the power of exascale computing. So the first stage of the ExCALIBUR program is to have several working groups focusing on various software to investigate a wide range of problems using exascale computing. So I led the working group on turbulent flows, and this podcast will help us to better understand how to efficiently use exascale computing to advance our knowledge of turbulent flow. So today my guest is David Ham, who is a reader in the Department of Mathematics at Imperial College London. David's research interest centered on the development and composition of high-level abstractions for scientific computing. And the reason why David is our guest today is because he's also the lead of an ExCALIBUR working group called GenX, which is focusing on exascale continuum mechanics through code generation. So good afternoon, David.
Good afternoon.
So I'm going to start my questions, and my first question is, please, can you tell us a bit about yourself, where you're from, what you have studied and where, and any previous positions?
Sure. So I'm actually originally from Canberra in Australia, and I studied my undergraduate degrees at the Australian National University in Canberra. I studied mathematics and law, which is a slightly less unusual combination in Australia than it would be here. And I nearly gave up the law stuff. I still do a little bit of law, but I mostly went on with maths. And I went on to a PhD in numerical methods for ocean flow at TU Delft in the Netherlands. And when I finished my PhD there, I moved to Imperial's Department of Earth Science and Engineering as a postdoc, still writing ocean models. And sometime after that, I got a research fellowship from the then newly established Grantham Institute for Climate Change at Imperial and started working on cogeneration problems. And that was followed up by another research fellowship, this time from the Natural Environment Research Council in the United Kingdom. And I moved on then into the Departments of Computing and Mathematics jointly at Imperial. And then eventually I landed a position as reader in computational mathematics, or senior lecturer, now reader in computational mathematics in the maths department, where I run something called the Firedrake project, which is a code generation system for solving partial differential equations by the finite element method. And I also run the math side of Imperial's Joint Maths and Computing program.
Wow, fantastic. So now that you have been at Imperial College for quite some time, I just wanted to ask you, what's the best thing about your current position and about working at Imperial College?
Easily the best thing about Imperial is the people who are at Imperial. So at Imperial, you have an absolute host of really amazingly talented colleagues to work with. The collaborations among your colleagues are brilliant, but also Imperial is a very attractive place for people to come study. And so our students are really brilliant. And in particular, our PhD students, who of course as a researcher are the ones who you work with as colleagues, are outstanding. And so the PhD students and staff who I get to work with are definitely the highlight of being here.
Great, thank you very much. So you said you've studied mathematics and law in Australia. So I was wondering, how did you become interested in high performance computing?
So I didn't study computer science at all as an undergraduate, although I've sort of eventually morphed into sort of halfway a computer scientist. But already when I started doing my PhD, it was very clear if you're building ocean models and you're interested in not just the numerical analysis, but also the practical implementation, that performance and parallelism are absolutely critical parts of doing that. And so I started to get interested at that point, but then it was really when I was at Imperial and starting my research fellowships, when I had the opportunity to spend more time and to supervise students focusing on fine details of what it takes to run efficiently in parallel, but then also at higher levels, the mechanisms we can use to generate the algorithms and implementation that will more effectively use parallel computing. Because there's two things to parallelism, right? One of them is to have an algorithm that effectively exploits parallelism, and then you need an implementation of that algorithm which is effective, and both of those are absolutely critical and become ever more critical the larger scale we go to. In fact, one of the things that's maybe a little bit neglected when we think about exascale is that as well as changing our implementations in order to exploit ever larger machines, we actually need to keep looking back at our algorithms and changing the core algorithms that we're using as well.
Wow, very interesting. So you said you are working with Firedrake, and I'm going to ask you some question about Firedrake, which is the framework you are working with. But I wanted to have your opinion on. So we are in towards the end of 2020, and if you have to solve partial differential equations on a supercomputer, what do you think, as of today, is the best strategy to do so?
So I think that when you talking about solving PDEs on a supercomputer, essentially you are after a certain level of accuracy given the resource that you can expend. And we more or less on a supercomputer have two sorts of resource constraint. We have operation constraints, so the rate at which the processors can execute the instructions that we feed them, and we have communication constraints. And the communication constraints are both the one we traditionally think of, which is across the network, but also the rate at which you can feed operands from memory onto the processing units. And if we look at the different techniques we use, I mean, essentially we have in our discretizations, two knobs that we can turn. We can make the mesh more fine, or we can make the degree higher. And there are algorithmic feed-ons from that into, for example, how do I then solve the linear systems that end up inside my Newton iteration at the end of the day. And so the hitherto dominant mechanisms have normally been pretty low order. So people either using finite volume methods, typically staggered finite volume methods in fluids, or they're using mixed finite elements, which are morally quite similar, and typically those finite elements are relatively low order for the workhorse bulk codes people are using. And what low order methods do is effectively turn bandwidth into accuracy, because the number of operations that they do per operand is not going to keep any current processor busy. So what you're effectively doing is streaming operands through your processors as quickly as possible in order to have more accuracy. And we typically implement those methods using explicit matrices. So we actually build the sparse matrices, and then we hit the sparse matrices with a suitable solver, an algebraic multigrid solver possibly. And those explicit matrix solvers are also basically bandwidth machines. They are not doing very many operations per operand, and they're basically streaming through. The challenge with that is that recent hardware has gone in the other direction. So actually, what we've got an awful lot more of in recent years is a lot more capability to do floating point operations, particularly if you can parallelize them well at fine grain levels, so at vector lane levels, whether those are vector lanes on a GPU or the long vectors on modern CPUs. And low order techniques with explicit matrices are never going to exploit that. They're always going to be choked by the rate at which you can feed the information onto the processor. And so I think that the interesting algorithmic move now is to get better at using high order methods, so high order polynomials to represent your spaces, and to use then the right matrix free preconditioners with the high order methods, so that we have a mechanism for turning floating point operations into accuracy rather than turning bandwidth into accuracy, because floating point operations is what we've got an awful lot of on current and upcoming machines. That said, I mean, we have to shout out the. I'm probably getting way ahead in the tour here, but there's a machine currently in the UK called Isambard at the University of Bristol and run as a consortium. It's one of the UK Tier 2 machines, and that machine is predominantly ARM chips. And what do they have? They have an awful lot more bandwidth. And actually, if you just take, for example, Firedrake onto that machine, it'll just run faster. And it just runs faster because we can feed the CPUs more data. And so what would be really, really exciting would be if the hardware technology could move more in the direction that ARM has taken it than in the direction that essentially everybody else has taken it.
Well, it looks like the Japan is listening to your recommendation. I mean, they have a very powerful computer now based on ARM technology. You mentioned briefly Firedrake. So can you tell us more about Firedrake?
Sure. So what do we do when we solve a PDE? So you start off with a set of equations and you decide how to discretize those equations, and then you actually apply that discretization, and that produces effectively a set of difference equations, and you use that to work out what individual floating point operations should be done on each operand to make a residual or a Jacobian, so a matrix or a vector, sparse matrix or a vector. And in the traditional approach, having done all of those things with a pen and paper, now we write code. And we write code that loops over arrays and does floating point operations on arrays in a language like C or C++ or Fortran, one of these languages that's directly compiled. And that's the thing that we compile into our code. And then if we need to, for example, vectorize, then we rearrange the loops in our CLC Fortran code, and we apply pragmas to those loops to try to tell the compiler to loop them correctly. Or maybe we use vectorized data types, but we do that directly in the code. And what that means is that the piece of code you've got is a long, long way from the mathematics, and is also quite tightly tied to the algorithmic and numerical analysis choices that you have made. And so if you want to debug it, or you want to change it, or you want to go to another piece of hardware, then you have to mentally decompile this back up to a more mathematical level, and then you can make your changes. And that's incredibly labor intensive. And it also demands a skill set of the people who are working on these codes, that basically every individual working on the code has to know everything. They have to understand the entire stack, because anything you touch in the code can break anything from the parallel performance to the numerics. And that's great if you have an infinite supply of geniuses who can work 24 hours a day. And meanwhile, us mere mortals would actually like to make some contribution here. And so what Firedrake is, and indeed what in many respects the other Gen X codes are in their own ways, are a statement that says, well, actually, this series of transformations that we did from the equations down to the code are, there is a mathematics that you're expressing about how to do this. So you substitute these things for these things, you solve an optimization problem for the right loop layout. And then what we do is we execute all those steps by hand. Well, actually, if we can specify those steps mathematically, we can write a computer program to do it. Mm-hmm. And in fact, really what you're doing is you're writing a compiler to do it, because what a compiler is a machine for taking one mathematical representation into a lower, more primitive mathematical representation. And so Firedrake is really a stack of compilers, the first one of which turns vector calculus into tensor algebra. And then we have one that turns tensor algebra into loops. And then we have a loop manipulation engine that can turn the loops inside out to parallelize them, whatever. And then eventually you end up with C, and we give C to a compiler, a conventional C compiler. So GCC, Clang, whatever the one that comes with your supercomputer is. And what that does is it means if you're somebody who wants to solve a PDE, you write down the PDEs. You write down Python code that feels like you're writing Mathematica. So you're writing down gradients and integrals, and you're specifying linear solvers in terms of the maths that they're going to do, not in terms of the calculations that they're going to do. And if, on the other hand, you're a computer scientist, so I have an incredibly long-running, very productive collaboration with Professor Paul Kelly, who's a compilers professor at Imperial. And he and I have had quite a number of computer science PhD students who are doing their PhDs in compiler theory and advances in compilers. And as far as they're concerned, it's the other way up. So they can study complex compiler problems because Firedrake is effectively a machine that feeds them compiler problems, and it takes away all of that nasty vector calculus and higher maths that isn't their territory. And of course, it means that rather than them solving toy problems, they're solving real problems that come from real users. And conversely, when they make an advance, it goes straight to the users. And so so effectively, Firedrake is a collaboration engine that means everybody in the stack can use more sophisticated and more high performance algorithms than they would be able to do if they were just working in whatever their expertise slice in this stack is. So that's what we do.
Fantastic. That's pretty impressive. So you mentioned the Gen X ExCALIBUR working group, which is obviously focusing on the same type of stack as you have in Firedrake. So what are your main goal for this Gen X working group in the next few months?
So like all the working groups, there's two aspects to what we're doing. We are doing something now. This is the demonstrator applications, and we are working out what the community needs to do looking forward. So if I look at the demonstrator applications, first of all, so one of the key advantages that we think that our approach has is composability. So it enables you to put together complex processes in ways that would be very person intensive to do if you did them by hand. So we actually then have wrapper layers around the outside of Firedrake for problems where solving a PDE is just part of the problem. So for example, if you have a nonlinear problem like flow problems, you can have multiple stable solutions. And some of these multiple stable solutions have been observed in physical wind tunnel experiments. And so if you're going to find the multiple stable states of flow over a wing, for example, what you do is you solve for one, and now your numerical solver is giving you an answer. So now you need to change your equation so that that one is no longer an answer, and your nonlinear solver will then find another one. This is a technique called deflation. And you can do that with Firedrake. And if you're doing deflation, it causes you to have to solve many PDEs at once. Similarly, if you want to do uncertainty quantification, you can wrap an uncertainty quantification layer around Firedrake and solve many problems at once. Or if you need to solve an inverse problem to optimize design parameters, then you need to solve many realizations, and you can do that once. So what we're doing is we're demonstrating that by combining Firedrake with the outer loops, we can achieve very large scale effective use of supercomputers to solve complex problems of the sort that scientists and engineers really want. So almost always, in fact, a scientist or an engineer wants more than just a simulation. They want a simulation as part of a process that they're studying. And so our demonstrator apps are designed to demonstrate that the sort of approach that we are taking is viable at those very large scales. And then the flip side to that is Firedrake and DeVito and OP2 can do what they can currently do. And sometimes the difference between that and exascale is just implementation and going and finding the bottlenecks and killing them. But actually, it's also incredibly likely that the current capabilities of the code generation ecosystem don't actually match what science and engineering requires in order to get real science outcomes from exascale computing. And because it's very easy for those of us who kind of working close to the software to be very, very happy about achieving a big proportion of peak on a very big chunk of a machine. But no one outside high performance computing cares about that, right? What the people outside high performance computing care about is that we get more efficient aircraft or better wind turbines or a better weather forecast or a better climate prediction. And so we will be running engagement activities, including one in 2 weeks' time, in fact, to try to work out from the wider community what it is that we can't currently do that, if we could do it, would enable then actual real exciting science advances at through very large scale computing. And so then the upshot of that will be the plan looking forward for what it is that code generation platforms need support to develop in order to deliver that for the wider science community.
Fantastic. I will actually be joining you in 2 weeks' time for your meeting. So I'm looking forward to it. I wanted to ask. I mean, you mentioned this already briefly in your at the start of this discussion, but I'm going to ask you again. I mean, if there is one thing about high performance computing that you could change, what would you change? So you mentioned already that you would like to see more certain type of hardware, but if you could change something today, what would you change in high performance computing?
So I think that if we're just talking about the high performance computing platforms, I think actually the really big thing that I would like to see come, and it's just always been for the last at least 5 years, it's just been about to go mainstream, is containerization. So if you are, like we are, effectively a software vendor, then from a user perspective, the software environment on supercomputers is an absolute nightmare. And it requires essentially vendor intervention from whoever your software comes from in order for you to get it up on a new supercomputer. And this applies to us. We deal with plenty of users who are running on British, American, other supercomputers around the world, and we have to keep diving in to help them. And it's because the platforms are so heterogeneous. So they have set up, here is the compiler over here is the special MPI you have to use or you won't get our fast interconnect. And also you have to have the right versions of all of these things lined up, and it's a nightmare. And so the promise is, of course, that once containers become sufficiently robust and are deployed at all of these supercomputers, then we can have our own little happy Firedrake environment where things just work, and that is deployable out across all over the place. And that would reduce my workload, but actually much more importantly, it would make the accessibility of large-scale computing to a broader range of science applications much easier, because I think actually that's one of the biggest problems we have as we go to scale. It will definitely be the case that huge hero projects, so things like nuclear fusion or weather and climate forecasting, where solving this one problem involves a whole building full of people, they will manage to make a large supercomputer work. But if they are the only people who can do that, then we will actually miss out on most of the science advances that could be delivered. Because actually, exciting cutting edge science is typically done by a very small number of people. Whether it's a university research group or people in a company somewhere, it's typically little groups of half a dozen people. And so the productivity of those people, the ability of those people to do impressive things for small amounts of their hours is absolutely crucial. And things like code generation are a part of that story, but there's also a platform part of that story where the platforms have to become easier to use.
Great. It's very interesting point of view. Well, I guess this is a connected question. I mean, we are going to have access, well, when I say we, I mean probably in the US or in China or in Japan. We are going to have access to exascale computers possibly in a year or two. Do you think the community is ready for the transition to exascale?
Most of it, no. So if you look at the number of applications that can usefully use a petaflop, it's a tiny minority, right? So petaflop applications doing real science exist, absolutely, but it's way from being typical. And when you go 1,000 times bigger than that again, then it's minuscule, right? So and even the sorts of organizations that I just mentioned are typically not in a position where their current code scales out there. So if we took the Met Office as an example, the Met Office are unlikely to run a single run at exascale, but the Met Office, the nature of the problems they do is such that they need to run ensembles. And it is entirely plausible. Yep. You can do the maths and say, if we want kilometer global scale, medium range weather forecasts in the right size of ensemble, you get to an exascale pretty easily. And so they've got the problem that will do it, they've got the resources that will do it, and they don't yet have the code that will do it. They might have the code that will do it by the middle of the coming decade. And so I think in many cases, even the people who are best equipped to do it are not there yet. But then that is, of course, the point of projects like ExCALIBUR, which is what is it that would take us from here to that position.
Great. Thank you very much. Is there any trend that excites you these days in high performance computing? I guess you mentioned the IRM in Bristol on the tier 2 system, but is there anything you like, oh, that's an interesting, that's a new interesting thing that I would like to explore?
That's a very interesting question. So, I mean, I think actually so in many respects, I actually think that especially the hardware innovations that have happened have actually more or less happened despite the needs of the HPC community rather than because of them. And so, and in many cases, like why aren't the clock speeds higher? The answer is, well, physics. So where so it's not that our needs were not taken into account. It's that what we'd really like turns out to be physically impossible, and that's unfortunate. But then also, I think that there has been a certain level of investing in technologies that might get you to an exascale, despite the implications of that. So I think things like long vectors are like that, right? So long vectors are a very effective mechanism for increasing the floating point performance of chips at the cost of programmability. And I think it's a very telling and interesting stage that, for example, Archer 2, because it's AMD and not Intel, is AVX2, not AVX512. And in fact, Archer is not accelerator based. Archer 2 is not accelerator based. Why is Archer 2 not accelerator based? Because the user community said, do not buy accelerators, we can't usefully use them. Yes. And so I'm happy to see that like the UK in making procurement decisions has made procurement decisions that are the sensible ones. I mean, I guess from a pure HPC technology perspective, they are also the boring ones. They tell you that what works, what we want as a platform that will enable us to do real work, are sophisticated processors with relatively high single thread performance per processor, and as the ARM demonstrates, high bandwidth per processor. And because those things are programmable and also robust. So I think that many of the programming models, and so the wide thread programming models for things like CUDA are a good example, but threads are another good example. Many of the programming models are sort of being pushed as saying, well, we can get right up to the machine peak by using them, also turn out to be not very robust. So in the many of those approaches, if you make small deviations from the optimal algorithm, your performance crashes. Whereas the multi-process explicit communication MPI model turns out to be vastly more robust. And so if you do most of the right things, you get most of the performance. And as you make changes, you're much less susceptible to your performance completely going off a cliff. And I think it's interesting that if you look around for examples of very high performance toy models using what might be termed kind of latest programming models, they're a dime a dozen. And if you look for very high performance, sophisticated applications that can do hard science or engineering, they are almost non-existent. I think that's also very, very telling. So what I think is always the future are mechanisms that enable people to combine approaches very effectively, because that's what gets you sophistication. And in fact, the big shout out I put out there is to PETSI. PETSI, a project which is now 25 years old. Mm-hmm. So not in that sense novel, but actually constantly novel in what they're doing. And the magic dust in PETSI is always composability. If you look at under the hood of PETSI, everything they do is based on the ability to arbitrarily combine all of the building blocks in PETSI to do what it was that you wanted to do in a sophisticated and performance way. I'm very biased here because, in fact, Firedrake uses an awful lot of PETSI under the hood, and we benefit enormously from what they're doing. But it's nonetheless something that we are always incredibly happy about, and we're incredibly happy about the advances that they make.
Thank you very much. Thank you very much. I have one last question. I don't want to take too much of your time. Can you give us a name for one of the future episodes of this podcast focusing on, well, turbulence and exascale? Yeah, if you think we should invite someone to.
Well, I mean, so this is very nepotistic because he's from my consortium, but you should absolutely be talking to Peter Vincent. So the work that they are doing on turbulent flow and the using PyFR is absolutely spectacular. Yes. And also they've done some actually really exciting visualization stuff connected to that. Their in situ visualization stuff is very nice and much better at producing pretty pictures than me. So you can have some of those in that podcast.
Fantastic. He is on my list of guests, Peter. So I will record an episode with him very soon. Anyway, thank you so much for your time and your input. It was very nice to talk to you, and we wish you all the best with Firedrake and with your Gen X ExCALIBUR project. That's it for today. So if you want to learn more about the UK Turbulence Consortium and our ExCALIBUR working group, you can check our website, ukturbulence.co.uk. We also have a Twitter account at UK Turbulence in one word, and all the podcasts that are going to be recorded will be made available on the UK Turbulence Consortium website. Thank you very much, David. And that's it for today. I hope to see you soon in one of the next episodes.